Now we are on air. So, hi everyone. I will give a little brief in Portuguese. Então, pessoal, esse é o Patrick. Ele é o estudante de física, matemática e também mecânica quântica lá da Universidade de Toronto. E é muito interessante o que ele tem para compartilhar com a gente hoje, então vamos prestar bastante atenção. Qualquer dúvida que vocês tiverem no inglês, tentem anotar alguma coisa assim, e aí eu passo para ele. Okay, now it's your turn.
Yes, hello. So my name is Patrick. I'm currently a student at the University of Toronto in Canada, and I'm studying physics and mathematics. So what I'm going to be talking about today is I'm going to give a brief overview of some classical cryptography and classical information theory. And then I'm going to get more into quantum information theory and quantum cryptography. In particular, I'm going to talk about a few different quantum key distribution protocols and different ways that quantum key distribution is being applied today, and how it's being implemented to do some actual cool things in the real world right now, and how it's a very exciting field. So without further ado, I'll switch over and yeah, I'll start up my presentation, I guess. Let's see. Can you guys see this?
Now it's working well.
Excellent. All right, so yeah, so I'll be talking about quantum key distribution. So the first thing I want to talk about is classical cryptography, which I'm sure you guys are already familiar with a lot of the important subjects in classical cryptography, but I'm just going to give a little rundown so we're on the same page with this. So first of all, the really big thing is that we want to know is, well, why actually do we do cryptography in the first place? And you can basically break that down into four main goals that you have for cryptography. The first one's kind of the most obvious one. You want to keep information confidential. So when you're sending information from one party to another, what you want to do is you want to make sure that only the intended recipient is the one that can actually understand the information that was sent. So you want to prevent everyone else from being able to read what is actually sent to the intended recipient. Sort of classical goal of cryptography. That's why you see in the Second World War, people sending secret messages so that spies wouldn't be able to know what they're talking about and things like that. But that's only one of the different things that cryptography actually does. The next big thing that it's really used for is data integrity. And so that's basically to make sure that the information that you're sending from one party to another doesn't get changed on the way. And that's really important because if, for example, you're downloading let's say you have an iPhone and Apple sends you an update to your phone, you know that Apple sent it to you, but you want to make sure that the update that was sent to you wasn't tampered with on the way, because then you could have someone, say, injecting malware or whatever so that your devices would be compromised. So you really want to be able to make sure that when someone's communicating with you, the message that they send and the information that they send doesn't get changed along the way. And that's kind of the main idea of integrity. The next thing is authenticity. So of course, if I'm communicating with you, I want to make sure that you're actually the person on the other end of the line. You want to make sure that the person you're communicating with really truly is that person that you think you're communicating with. And this is really important for everything. In fact, you can kind of know that confidentiality and integrity, you can't actually have those if you don't have authenticity. To kind of demonstrate that, if you don't have authenticity, and let's say you've got two people, say Alice and Bob, they're sort of the classic example of people that communicate in these cryptographic schemes. If you have Alice sending a message to Bob, her message can't be confidential if someone can jump in and say, oh, by the way, I'm Bob, right? So you want to be able to trust who's on the other end of the line. Otherwise, you really can't establish any kind of secure exchange of information without authenticity. Then the other major goal of cryptography is called non-repudiation. And this one's a little bit more subtle. Essentially, what you want to do with non-repudiation is you want to make sure that any user who makes some sort of agreement or who has some sort of action in the past, in the future can't deny having made that decision in the past. So if someone appends their signature to something, then it needs to be possible for any point in the future for someone to say, no, you signed this agreement, you have to do what this agreement says. It's a bit more of a subtle point, but it's also very important. So those are kind of the four main goals of cryptography, both classical and quantum cryptography. That's kind of what you want to do with these technologies. So I'm going to go over some of the basic fundamentals of classical cryptography. I'm sure you guys have seen this all before, but there's basically two main kinds of classical cryptography. There's symmetric key encryption, and then there's also public key encryption. I won't go into very much about public key encryption, and I'll explain why in a little bit, but so I'm mainly going to focus on symmetric key encryption. But the main idea of symmetric key encryption is you've got a whole bunch of messages that you could possibly send. So you could look at all the different strings of texts, or I guess equivalently, all the bit strings that you want to send from Alice to Bob. So those are your plain text. Those are the messages that you want to send. Then you also have a set of all the different possible ciphertexts that you could add. So this is the set of all the different things, all the different possible encryptions of your messages. And then what you have is you've got a set of possible keys. And basically what you do is you can take a key, which would be a random string of bits, ideally, and you could XOR that with your message. I think you guys probably know about XORing, but it's just the whole idea of if 0 XOR 0 equals 1, 1 XOR 1 equals 1, 0 XOR, or sorry, I think I got that backwards, but it's kind of pretty straightforward. But you can basically XOR a key with your message, and that will essentially scramble all the information. I'm sure you guys are familiar with this already. Then the idea that you have is once you've got two parties, Alice and Bob, that share a secret key, then what Alice can do is apply some sort of function, we'll call it EK, and you can apply EK to the message, and what that'll do is that'll create a ciphertext. And then Bob, on the other end, will have a decryption function, which is essentially the same. It's essentially the inverse of the encryption function, where you can apply that to the ciphertext and then recover the message. And the idea here is then anyone who intercepts the ciphertext won't actually be able to gain any information about the message. Of course, there's the important condition that you have to be able to use the decryption function to recover the message from the ciphertext. But again, this should all be review. Yeah, so that's sort of basically the rough schematic of symmetric key encryption. You start with a message. So the two parties share a key. One party wants to send a message to the other, so they encrypt it using their key, and then they send the ciphertext, which appears random to any adversary. And then on the other end, the recipient then uses the same key that they had in the beginning to decrypt the message. Very, very straightforward. And so this is what we see here. So you need to have a secret, you need to have a secure channel in the first place by which you can send the key that they're going to share. Otherwise, if some adversary, we call the adversary Eve because Eve could be an eavesdropper. It's just sort of the classical way of doing it. But so in order for the two parties, Alice and Bob, to agree on a secret key, they first have to be able to send the secret key over a secure channel. That's technically the most difficult part of classical encryption is actually sending a key from Alice to Bob, because if you have a perfectly secure channel where Alice can send anything she wants to Bob to form a key, then you might as well just send the message over that line in the first place. So this is kind of the most difficult part of classical encryption, is establishing this secret channel over which you can send a key from Alice to Bob so that they can agree on the key that they're going to use for their encryption. But once you've agreed on a key, then it's very straightforward. Alice chooses her message and encrypts it with the key, sends the encryption, the ciphertext to Bob over a public channel and insecure channel. So the idea is you want to be able to send the ciphertext in such a way that an adversary, Eve, would be able to read the ciphertext, tamper with the ciphertext, do whatever they want, such that when it gets to the other side, Bob would be able to recover the message, and importantly also know if the message has been tampered with along the way. Sort of the most basic form of symmetric key encryption is called the one-time pad, and that's basically the idea of you create a random key the same length as your message, and you share the random key over a secure channel between Alice and Bob. And then Alice encrypts her message of the same length as the key that they share and sends the ciphertext to Bob, and then he can then decrypt it. And you can show mathematically that this is in fact sort of perfect security. This system, theoretically, if you can establish a secret key, is sort of the ideal way to distribute, to perform classical encryption. There, you can't really, you can show that it isn't possible, even in principle, if this is implemented correctly, for any adversary to actually attack this protocol. So the one-time pad is actually a very, very powerful notion. It's just very difficult to implement because, again, you need to be able to establish a secure channel where you send the key in the first place. So that's kind of the biggest problem that those have, is being able to send a key from one place to another. And because of that, lots of very interesting but kind of convoluted encryption protocols have been created to try and allow you to send things over channel, like a key over a channel that's not actually totally secure. So that's kind of the big difficulty with classical encryption. I'm going to talk a bit about the different kinds of security that you want. So the most practical and basic kind of security, sort of the weakest type of security that you could have, is called computationally bounded security. So this is the kind of security where you assume that your adversary can't learn anything about the ciphertext in a certain period of time if you assume that they have a certain number of actual computers. So you might be that they're running it off of you might want it to be that they can't learn anything about your ciphertext in 10 minutes on their Dell laptop, or it could be you don't want them to learn anything about your ciphertext in 100 years on a supercomputer. So you can specify those parameters, but that's kind of what limits this kind of security is. It doesn't say that it's impossible to learn anything about your ciphertext. It's just that your protocol needs to make it such that in a certain specified amount of time, certain computational power is not sufficient to learn anything about the ciphertext. So that's computationally bounded security. And practically it's quite powerful right now, but theoretically it's really not all that secure, because if, for example, you assume that they won't be able to break it in time t with x many real computers. If they have x+1 real computers and they have an advantage over your schematic, and they can in fact learn something about the ciphertext, even if you don't think that they can. So computationally bounded security, practically, it's much easier to achieve, but it definitely has a lot of serious problems theoretically. A slightly stronger kind of security, well, a substantially stronger kind of security is semantic security. So the idea of a semantically secure protocol is that if you have any polynomial time computer, the adversary can't actually learn anything about the plain text with greater accuracy than making a random guess. So this means that if they've got the thing is, essentially all computers right now are polynomial time computers, which means if you give it an algorithm to run, it can run an algorithm with a certain number of parameters. It can run it in a time that's proportional to some polynomial of that parameter. So like, let's say you have a parameter x, then you would say that the time that it would take to compute something would be like proportional to, say, x to the 3, x to the 3, or like x to the 4, or x to the 5, or 6x to the 7 plus 18x squared plus 9, or like you can form a polynomial that represents how much time it takes for it to guess something. So that's how all computers necessarily run classically. So semantic security with classical machines is essentially ideal perfect security. You can't actually break semantic security if you have just regular old computers that we use. Even if you've got a huge amount of time, you still can't learn anything more about the message that was sent with any better accuracy than if you would. Pardon? Sorry, I'm not sure what that was. The idea is you don't want to be able to learn anything about the plain text better than a random guess. Or sorry, you don't want the adversary to be able to learn anything about the plain text better than a random guess. And semantic security says you can't do that with a polynomial time machine. By far the strongest form of security is called information theoretic security. And information theoretic security is basically the type of security where you can say, my adversary is allowed to have infinite computational resources. It doesn't have to be polynomial time machines, but it could be, for example, like exponential time machines, or like essentially you could imagine a computer that can perform an infinite number of calculations in 0 seconds, in exactly 0 time. If you can have as much computational resources as you want, as much time as you want, and then the idea of information theoretic security is that even under those incredible ideal conditions, the adversary still can't guess anything about the plain text better than a random guess. So this is really powerful because it means no matter what your adversary has, it's not just restricted by current technology, but any hypothetical technology in the future, no matter what, your adversary still can't learn anything about the message that was sent, which essentially means perfect integrity, perfect confidentiality. So this is really a powerful idea. The problem is it's very, very challenging to implement. In fact, you can show that with classical cryptography, it's actually possible to implement. One-time pads are information theoretic secure, but the problem is you need to be able to distribute a key before you can implement one-time pads. And this is the problem I mentioned earlier. If you can send a key over if you can establish a key first over a secure channel, then you might as well just use that channel to send your message, and you have no need for cryptography at all. So one-time pads are information theoretically secure, but actually implementing them in a perfect way is very, very challenging. In fact, it's impossible, given, I'll say, classical technologies, classical computers, classical systems. You can't actually do that. So that's kind of the big difficulty. The other thing is, this is why I didn't really want to spend any time talking about public key encryption schemes, is that you can actually prove mathematically that no public key encryption scheme is information theoretically secure. So you guys might be familiar with some public key schemes like RSA or Diffie-Hellman public key protocol, things like that. Schemes like this essentially rely on the fact that your adversary isn't able to factor large numbers quickly. It's known that factoring large numbers is computationally a very, very difficult problem for a computer to do. So those systems essentially are computationally bounded secure. Granted, the numbers that a computer has to factor in order to break RSA encryption, for example, are huge. So like it's unfeasible for anyone to try and actually break RSA encryption using classical machines, because it literally takes years for them to break even a single key from top of the line RSA encryption, which essentially means that it's not actually reasonable for them to try and do anything better than computationally bounded security, because there's really practically no need. If you're using RSA to send every single message that you ever send, and everyone's doing that, there's just so many keys that exist, and everything moves so quickly that it's unreasonable to try and actually break it. So currently, public key schemes work given current computing power, but theoretically speaking, they're really not secure. And they're what we use for everything, essentially. So really what this means is that current cryptography, but really all of classical cryptography, is not information theoretically secure. And more importantly, it can't be. Given the laws of, I'll say, classical physics, classical computation, classical information theory, given all of this stuff, it's not possible for you to create an encryption scheme that actually is information theoretic secure, which means it's always possible for there to be some kind of adversary that can break your system, which is really quite unsettling, given that everything that we do in today's society really is based on our ability to do cryptography, because everything that we do, all of our banking information, every email we send, every private message we send to anybody, all of the information about our lives really does hinge on, at the very least, the integrity of data. You want to make sure that people can't tamper with how much money you're sending to someone else, or like even authenticity. You want to be able to identify who it is you're actually sending your private emails to. So everything in current technology, current society really is very fundamentally based on the idea of having secure means of communication. But theoretically, that's not possible with classical cryptography. So this is kind of a big problem. Not right now, because right now we're protected by the fact that our computers are essentially very slow. They're polynomial time computers. And so we're sort of protected by semantic security and computationally bounded security for now. But we can envisage a world where that's not actually the case anymore. We can very easily imagine a world where other things, in particular quantum computers, which I'll get to in a little while, this is why it's really, really important for us to consider how to kind of get around the issue of classical cryptography not being information theoretically secure. And we really want to make things information theoretically secure. Yeah, so that kind of wraps up my brief summary of classical cryptography. I know I'm missing out on a lot of details, but that's essentially enough to get the picture of where we're going. So now I'm going to get into a little bit of quantum mechanics. And what I'm going to say before I dive into this is that quantum mechanics is essentially physics, but it's a very unusual kind of physics. We're not looking at, given a certain initial velocity and a certain acceleration, how far a ball will move at a given trajectory. We're not looking at anything like that. It's not that kind of physics. It's much more strange and much more interesting. I would say it's a much more rich field to study than all of those classical mechanical systems, but it's essentially physics. But the cool thing is it's physics that is very counterintuitive and breaks a lot of the rules that we would expect of nature. Yeah, so I'll get into that now. So I'm not going to go into too much of this, and I'm not going to use too much rigor because it gets very, very complicated, very mathematical, and very counterintuitive very quickly. Just give a brief overview of some of this stuff. So we see the biggest difference between classical mechanics and quantum mechanics is that we express, for example, a particle. If you imagine an electron or any kind of particle like that, we express the state of every object like that, or even collections of particles, or any kind of system. We express the state of that system by like a vector. And by a vector, I don't mean like a velocity vector or anything like that. I mean a very abstract vector. Specifically, it's a vector in an infinite dimensional Hilbert space, which I'm not going to go into that, but basically we take all the information about the system in the physical world, and we try and abstract that into the mathematical world to a point where it's not actually as intuitive as things usually are. And sort of how we define these vectors is we say that mutually exclusive values of a given physical property correspond to orthogonal state vectors. So I'll just draw this out because it's a little weird. But if we've got a vector, say like that, let's say this vector corresponds to a position in space. So it could be that your particle that you're looking at is right here. And this is the vector that corresponds to that. Then if we see another, if we instead want to consider when that particle is here, the state of this second system is no longer this, because this is a mutually exclusive value. You can't have a particle be both here and here at the same time. At least you can never measure that. So you can't look at a particle and see it being here and also being here. So these are two mutually exclusive values of the property position. So consequently, if this is the state vector that corresponds to this state, then this state must correspond to something that's orthogonal, which would be a vector like this, where this is like a 90-degree angle, basically. And of course, this is a two-dimensional vector space that I've drawn here, only because I'm limited to a screen where I can't draw infinite dimensional things. But really, every point in between here is a unique point in space. And so we would actually have to look at this as sort of an infinite dimensional system where every orthogonal axis corresponds to a different state of this particle. And this is only corresponding to position. Of course, particles have many other properties as well. They have momentum, they might have charge, all these different properties correspond to different vector spaces that you sort of mix together. So it's much more abstract. But here's the weirdest thing. I said that you can't have a particle that's in two places at a time, and that's sort of true. Whenever you measure a particle, it will always be in one place or the other. However, before you measure it, that's not necessarily the case. It's possible to conceive of a particle that has a state vector that's like this. And what that essentially means is, you see this vector is partially pointing up, but it's also partially pointing sideways. So it's kind of part way in this state and also part way in this state. And we would call this a superposition state, because basically this is a state that's kind of both in this state and also both in this state. And this would correspond to a particle that's like simultaneously here and also here in space at the same time. So this is really weird, because now I'm saying we can have particles in the same place at the same time. But the catch here is, as soon as we try and measure where the particle is, we will always find that it's in one of these places and not both. So measurement actually disturbs the system quite substantially. A way to kind of conceptualize this is if you imagine trying to measure the temperature of something. The temperature, like, let's say you put a thermometer in a glass of water and you try and measure its temperature. Well, you don't know in advance if the thermometer is hot or cold. I mean, if you touch it, you would know, but that's beyond the point. If you were to just watch a thermometer be lowered into a cup of water and you were to try and determine information about the volume of that, or the temperature of that cup of water, then you would see that the measurement on the thermometer would change once it goes into the water. But what you don't know in advance is the temperature of the thermometer. If you've got a warm glass of water and you put a really, really hot thermometer into it, the temperature of the water is going to rise. So this very active measurement actually changes the state of the system. But the thing is, in classical systems like this, the thing I just described, you can essentially reduce the problem to making better and better measurement devices that have less and less of an impact on the system they're measuring. But in quantum mechanics, every single time you measure the system, you necessarily disturb it in a major way. So you can conceive of particles that are in this point, at this point, and at this point, and really at any point in space, really. It could be up here, it could be down here, whatever you want. It can be anywhere in space. And it can even be a mix of being in different places at a time. It's kind of spread out over space, more almost like a wave. That's why you hear people talking about things like wave-particle duality, for example. But it's kind of like the position is sort of, it's not localized to a single point, it's rather spread out throughout all of space. And then what happens is as soon as you measure it, it becomes localized to a single point. And so it's that active measurement that changes. And we describe measurements actually as they're called operators, and they're kind of like functions that act on vectors, because it's something that necessarily changes the orientation of the vector. If you measure this position state, you might see that this is what you measure. I mean, you might see that this is what you measure as well, but you'll measure one of those two, right? You'll never measure this state. You'll always measure one of these two states. And we call this it's called an eigenbasis, but we call it a basis, basically because it's the vectors that kind of create the entire space. So things can be simultaneously partway in this state and partway in this state, but these two states themselves are totally distinct. So they make up what's called a basis of this vector space. And so the thing is, if we have, let's say a particle is half, you're like half of the time you measure it, it's in this state, and half of the time you measure it, it's in, then that would correspond to this vector. And you call this kind of thing, you call this a linear combination or a superposition of states, because you'd get something that looks like this, representing the state of the system. And this is really abstract. I apologize, because I know that this isn't a quantum mechanics course, but this is just sort of some of the rough background that's necessary to really dig into quantum cryptography and quantum key distribution. So I hope that kind of makes sense. I've sort of rushed over a lot of it, I know, but I hope that's enough. So the biggest idea to take from this, we can kind of, actually here, I'll say something else. We can kind of look at these as bits, which I'm sure you guys are much more familiar with than Hilbert spaces, for example. So if we look at this vector as corresponding to 1, and this vector is corresponding to 0, then obviously, if you were to measure if you have a bit and you want to know what the value of the bit is, it's either a 0 or a 1. That's how you define a bit. But what's important is, in quantum mechanics, you could conceive of things, they're called qubits, and they can be in any combination of a 0 and a 1 at the same time. The thing is, as soon as you measure them, it's going to be a 0 or a 1, but they can be in a superposition of 0 and 1. So that's what really makes quantum mechanics a lot different from classical mechanics. And we'll see how that can be used and applied to cryptographic systems shortly. So here's an example. One property that we have, just to solidify things again, a major property of light, and we'll be dealing with this a lot more, is called polarization. I'm not going to dig into it too much. You can look at it as an orientation of an electric field in space, but there's no need to go into that kind of detail here. So you can look at it as basically like, if you have, in quantum mechanics, we do often describe light as particles. We call them photons. And here, we can basically look at, let's say that this point right here is a particle of light. Then if this is a particle of light, we sort of define a direction to it, and we call that the polarization. So the direction could be up like this, could be sideways like this, could be on a diagonal, could be on the anti-diagonal, could be anywhere in between. So these are the possible polarization states of the light. And then what we have here is we can create, there's a thing called a polarization filter that we can use. And what this basically does is it only lets light through if the light is pointing up. So this particular one, you can also, if you were to rotate this filter 90 degrees, it would only let through the light that's sideways. If you rotate it 45 degrees, it would only let through the light that's on the diagonal and that kind of thing. So basically the orientation of the polarization filter determines which polarization of light will pass through. So here, light of all these different polarizations can reach the filter, but only light of this orientation can pass through. So if we face for example, let's say there's a photon, a particle of light that comes in with this sort of diagonal polarization like this. And we see, let's say it makes an angle theta with the vertical polarization, which corresponds to the filter. So this is a vertical polarization filter. And we see that the beam that's coming in makes this angle with the vertical polarization direction. This angle then actually relates the probability, the cosine of this angle, sorry, actually relates to the probability of this light passing through. So we see if this light is totally perpendicular, let's say this light were like this and it were a 90-degree angle, then we would see that the cosine of the angle, cosine of 90 degrees, is 0. So there's a 0% probability of this light passing through, which makes a lot of sense, because if you look at a vertical line and a horizontal line, the horizontal line is in no way similar to the vertical line. Whereas if we look at the vertical line and then a line that's on an angle, there is kind of some I guess verticality to this line. There is a certain amount of it that is in the up direction. And that amount of it that's in the up direction relates to the probability of it being, I guess, seen by the filter as being in the up direction, if that kind of makes sense. I know I'm going over this again very quickly, but so basically the angle that it makes, and the thing is, as soon as this diagonal beam of light passes through the filter, what you see afterwards will be vertical. So the angle actually changes. So this light started being at an angle theta with the vertical beam, but when it goes through, it is vertical, because we defined this as only letting through vertical light. So that's kind of how this works. We can see this light as being a superposition of being horizontal and vertical. And so there's a certain probability of it being measured. If you measure it, there's a certain probability of it being vertical, a certain probability of it being horizontal. And that probability is proportional to this angle. Now I'm going to get into something that's a lot weirder. And I apologize if I'm moving too quickly, but this is really an important thing to grasp. It's called entanglement. There is a mathematical description of it that's been covered in vast detail in many different books. You can look at it as quantum superposition states. So here, when I use this notation, we can consider, let's say we're considering 2 bits. Okay, so we've got bit 1 and bit 2. And bit 1 can either be a 0 or a 1, and bit 2 can be a 0 or a 1. If it's an entangled state, then it's a superposition that can't be split up into, well, it can't. They're non-separable Hilbert spaces. But basically, what it means is that here, if we measure one of the particles, so let's say particle 1, let's say this one's particle 1. If we measure its bit value, if it's 0, the other one's also 0. But if we measure the first one to be 1, the other one's automatically a 1 as well. That's the state that we define in this entanglement system. Similarly, we can define the opposite, where if you measure the first one to be a 0, the other one's automatically a 1. If you measure the first one to be a 1, the other one's automatically a 0. That's a different entanglement state. But the key concept here is that the state of 1 automatically influences the state of the other one. So more conceptually, an entanglement state is a state that corresponds to multiple particles, such that the measurement outcome on one of those particles directly impacts the measurement outcome on the other one. Even if they're separated, even if you have 2 entangled particles on opposite ends of the universe, If you measure one of them to be, let's say the bit you ascribe to that particle, if you measure that bit to be a 1, on the other end of the universe, depending on the system, let's say it's this first system, if you measure the first one to be a 1, then you know immediately that the other one's also a 1. You don't have to do anything else. You don't even have to measure the other one. You automatically know that the other one's a 1, just by virtue of the fact that the first one was 1. Similarly, in this system, if you measure the first bit to be 0, and you look at the particle on the other end of the universe, it will also be 0, and it'll always be the same value as the first one if you measure them in the same basis. So basically what this is useful for is if we have two entangled photons, let's say we call it polarization entanglement, then if we measure the polarization of one of these photons, the polarization of the other photon will actually be the same no matter what. It doesn't matter where it goes, doesn't matter who has it, its polarization will be identical. And this is really important. One of the important things here is that if we measure, so let's say we've got this entanglement state again where both photons take on the same polarization upon measurement, then you can't predict in advance. You can't say that I want it so that they're both zeros, or I want it so that they're both ones. All you can say is I want them to be the same. And that's very important. So what will actually happen is when you measure the first one, you'll get a random result. You can't say it's always going to be 1. You can't say it's always going to be 0. Half the time you measure the first one, it'll be a 0. Half the time you measure it, it'll be a 1. But what's important is no matter what its measurement is, you know immediately that the other particle has the same measurement. And this is really, really important for cryptography, as we'll see in a moment. Now I'm going to mention a little bit about quantum computers. I'm not going to get too much into them. To be honest, I'm not terribly an expert in quantum algorithms or quantum computation, so I'm not going to get into too much of this. But the fundamental information here is that, so first of all, regular computers, of course, run with bits. Quantum computers run with qubits, which are essentially bits that can be in superposition states. So a classical computer, you've got a 0 and a 1. A quantum bit, you could have, say, a 0 that's this state, or a 1 that's this state. You can have a superposition where it's half, or anywhere along this circle, really. So that's the biggest difference. What's interesting about this, though, is that the state, if you've got an n qubit quantum system, then you can express that in terms of a 2 to the n dimensional vector, which essentially means that, so each dimension of this vector you could use to correspond to 1 bit of classical information, which means that n qubits holds the same amount of information as 2 to the n classical bits. And this is really important because I said classical computers run in polynomial time, but what this means is that quantum computers actually run in exponential time, which means they're not just a lot faster, but they get faster and faster as time increases. So if you're running an exponential computer rather than a polynomial computer, your computations will go by way quicker. They're like, if you want to do, say, 5 calculations on a polynomial time computer versus an exponential time computer, 5 calculations, okay, they might be comparable in time. But let's say you want to do 100. Then suddenly your exponential computer gives you a bit of an advantage. Or let's say you want to do 1,000. Suddenly your exponential time computer is much faster. And when you want to do things that require a lot of computing, like for example, factoring large numbers, which we know to be a computationally very challenging problem, then we see that exponential computers are able to do that incredibly fast, very, very quickly, faster than classical computers can do a lot of regular calculations. So this is really a big deal. In fact, this is kind of the reason why quantum cryptography became a big deal in the first place. In the 90s, a guy named Shor, who's I think a computer scientist and mathematician at MIT, so he doesn't have any physics background. He decided to learn a bit of quantum physics, and he decided that he would write an algorithm because he noticed that these whole qubit things were really interesting, and he decided to write an algorithm using them. And basically, he created a thing, it's called Shor's algorithm, and it's an algorithm for factoring large numbers in exponential time, very, very quickly. And that seems like sort of a basic mathy problem that doesn't have much of an impact on the real world, except for that we know that RSA encryption, which we use for everything, that essentially breaks RSA encryption, because RSA encryption requires that we're not able to factor large numbers in a short period of time. So Shor's algorithm, which is a very easy thing to run on a quantum computer, essentially shows that with a quantum computer, you can break RSA encryption very, very quickly, which means quantum computers are a serious, serious threat to classical cryptography. And so we seriously need to develop a solution to this if we want all of our cryptographic infrastructure to survive the revolution of quantum computers once they eventually take form. In short, we really need new cryptographic systems. And luckily, we see that quantum mechanics provides the issue. It's quantum mechanics that allows us to have quantum computers and that allows us to break classical cryptography. But what's really, really nice is that quantum mechanics also provides the solution. So here we can start getting into quantum key distribution. So in quantum cryptography, basically the easiest way to do this, to try and create a information theoretic secure system, so a perfectly secure method of cryptography, well, we know the one-time pad is perfectly secure as long as we can distribute a secret key, right? So basically, quantum cryptography just seeks to use the one-time pad encryption again, but allow us to exchange a secret key. So that's really the big deal, is that quantum mechanics actually allows us to exchange a secret key between two parties without anyone being able to interfere. Now, the caveat here is that the key that we exchange, we can't decide it in advance. It has to be a random key. That's actually really nice, but it means that we can't send a message using quantum key distribution systems. We can only send random bits, but those random bits, you can actually show that any adversary that tries to interfere with these random bits will be detected by Alice and Bob, and they know that their key is compromised, and they know that they can't do encryption with each other. So quantum cryptography essentially allows us to exchange secret keys that are random, such that we can do a one-time pad with perfect security, which is kind of a really big deal. So when people started looking at creating quantum cryptographic systems, they started to think about, well, what actually do we, like, we don't want to make the same mistakes that classical cryptography does. So we want to really make sure that we're taking absolutely everything into account. Consequently, when you formulate a quantum cryptographic system, you have to look at the capabilities of the adversary. First of all, in quantum key distribution and quantum cryptography, you always assume that your adversary has infinite capabilities as long as they're physically possible, which means any technology that you can imagine existing, as in any technology that's physically possible in principle, even if it's practically incredibly challenging to create, hasn't even been done in a lab ever, no matter how complicated or difficult it is to do, if it's physically possible in principle, we have to assume that any adversary has access to perfect technology that can do that exactly every single time with perfect accuracy. Second of all, we assume that quantum adversaries have infinite computing resources and speed, which means we don't want to put any sort of computational bound on them. We want to make sure that we're really making things information theoretic secure. So this means that you can consider a quantum adversary that has access to all of quantum physics that we know of and can use it in all these marvelous ways, but can also compute an infinite number of calculations in 0 time. So really, this means that they can do all sorts of incredible things. We have to assume that they have access to technology that does not yet exist. Because as long as it's physically possible in principle, we know that we might be able to have it in the future, which would mean that the systems we're creating now might be compromised in the future. And we don't want that. So we have to assume that certain technologies are available to any adversary, even if we ourselves don't have access to them. Some of the big ones that we have, some of the big technologies that are not actually available at the moment that we want to consider are a thing called quantum memory, which is basically the idea of like taking a photon or something and without disturbing its state, just holding it in place for a certain amount of time without messing with it at all. That's in the lab very, very challenging to do, but we know that in principle it's possible. We also have to assume that they have access to a photon number counter, which is, again, not something that we have practically implemented ever, but it's something that we know could exist in the future. It's a technology that allows you to count how many photons have gone past a certain place without disturbing them at all. So technologies like this that are allowable by the laws of physics, even if we don't have them or can't create them at all, we have to assume that the adversary has them. And that's kind of the starting point for quantum cryptography. So now we want to look at, well, how do we actually do cryptography using quantum mechanics? In particular, how do we see the only big problem is how do we actually exchange a key? So we're going to be looking at strictly quantum key distribution from here on in, because we know once a key has been established, you can do perfect encryption using the one-time path. So our problem really boils down to exchanging a key between two parties using quantum mechanics. So the most common way of doing this that's used in most systems, both in labs, in practical systems, in theory, they all essentially boil down to a thing called the BB84 protocol, which was invented, so the name is BB84, it's for Bennett and Brassard from 1984. So it's these two physicists who came up with this in the 80s, and it's named after them. So these are kind of the tools in the toolbox for creating the BB84 protocol. So you assume that the two parties, so we'll stick with using Alice and Bob. So Alice is the person who's sending a message, and Bob is the person she's sending the message to. So we assume that Alice and Bob already have an authenticated classical channel of communication. So this could be an authenticated line of communication over the internet, or a telephone line, or anything like that. As long as it's authenticated, as long as they know that who they're communicating with, then even if other people can read exactly what they say, if they have an authenticated classical channel, then that's good. And then the other thing is they also need a quantum channel. So the authenticated channel essentially means nobody can interfere with the line of communication, but everyone can read it. And the open quantum channel is essentially a channel of communication that uses quantum mechanics where anyone can read or write to that channel. So it's unprotected totally. Anyone can write to it. Anyone can inject their own information. Anyone can read exactly what's going through. It's totally open for anyone to do whatever they want to. But the important fact is that you need to be able to exchange information using quantum mechanics. So the rough protocol, and I'll go into more detail on this in a second, is that Alice sends some random bits to Bob, and then what they do is, and so they both randomly choose bases. Alice prepares the bits in a certain basis, Bob measures them in a different other basis. And then what happens is they both announce the basis choices that they made so that they know how to sort of figure out what their key will be. They sift their bits so that they have the right key. And then they carry out error correction, which is an entirely classical protocol. And I know that was very fast, but here's a much more descriptive image of what's going on. So here, so we see on Alice's side, Alice has a source of light, so like a laser or a source of photons, for example. And what she'll do is, so here she's got two different bases. We see, so if we ignore these bottom two, these first two, we call this the horizontal vertical bases. So we've got horizontal light and vertical light, or polarizations of light. And what we do is we define horizontal light to be a 0, like the bit that corresponds to the horizontal light is a 0, and the bit that corresponds to vertical light is a 1. Similarly, we've got this other basis it's called the diagonal anti-diagonal basis. And we see the diagonal polarization filter is defined to equal 0 as well. And the anti-diagonal polarization filter is defined to equal 1 as well. And so this is sort of our dictionary that we use. And Bob also knows this dictionary. He knows horizontal, vertical. He knows horizontal 0, vertical 1, diagonal 0, anti-diagonal 1. Like that's known by both parties. Furthermore, it's known by any adversary. It's known by our adversary Eve. It's known publicly. Everyone knows that. That's not a problem. And we see here that this, like for example, diagonal light can be looked at as a superposition of horizontal and vertical light. We see this is kind of like 50% horizontal light, 50% vertical light. Half the time, if you were to measure this in the horizontal vertical basis, we call this a basis. So we call these two a basis and we call these two a basis. half the time when we measure this light that's been polarized in the diagonal direction, half the time when we measure it in this basis, it'll be vertical, and the other half of the time it'll be horizontal. Same thing with the one. So with the anti-diagonal light, again, if we measure it in the wrong basis, half the time it'll be 0, half the time it'll be 1. So what that means is if light is prepared in one basis and measured in the other one, the bit that you get will be random. It won't be, there will be no correlation between the bit that was sent and the bit that was measured. So the protocol that they undergo for BB84 encryption is basically this. So Alice prepares light. So let's say she chooses a random basis, and she happens to choose the diagonal anti-diagonal basis. And then what she does is she sends a pulse of light. Then she randomly picks a bit as well. So she's randomly picked this basis, and then she randomly chooses a bit. So let's say she randomly chooses 1. So what she's done is she's randomly chosen out of the 4 different possible polarization filters to use this one. And she sends a pulse of light through that filter, so all the light that comes out the other side is polarized in this direction. So that corresponds to this beam of light. Now, let's say that Bob then measures so then what happens is once Bob gets this pulse of light, so all of these pulses of light will have to go through before this one gets there, but assume this pulse of light goes all the way across to Bob, and he now has to measure it. So now what Bob does is he randomly picks a basis. So half the time he'll choose this basis, half the time he'll choose this basis, like the horizontal vertical or the diagonal anti-diagonal basis. So let's say if he were to choose the diagonal anti-diagonal basis, then what would happen is he would measure this pulse of light that was sent. He would measure it in the same basis that it was sent. So let's say he measures it in this basis. He's measuring it in the same basis that it was sent, and so the bit value that he'll obtain will be the same bit value that Alice sent. Sorry. That's really important because that means that they then share the bit. Now, if he measures it instead in the wrong basis, let's say he measures it here. We see, so this is the light that Alice prepared, the measurement that Bob performed, and the bit value that Bob obtained. So Alice sent a 1, and Bob measured it in the wrong basis. He randomly picked a basis, and he chose the horizontal vertical basis, which is not the same basis that the light was prepared in. And he measured a 0. Now, what will happen at the end is they'll after they've sent a whole bunch of bits at the end, they'll announce which bases they've used for each bit. So here, Alice will announce that she used the diagonal anti-diagonal basis, and Bob will announce that he used the horizontal vertical basis. And so because they know that they used different bases, Bob will know that the bit that he obtained was random. So he knows that he doesn't necessarily, half the time he won't have the same bit as Alice, which means that they decide to throw that bit away. So here you see they don't actually have a bit in their key because they didn't agree on the basis that was used. Now let's try this again. So let's say that Alice instead chooses to prepare light. Again, she prepares a 1. Let's say she prepares this one. So she prepares light in the vertical direction, corresponds to this one. So the bit that she's sending is a 1. Now, when that light gets to Bob, he randomly picks a basis, and he happens to pick the right one. So he happens to pick to measure in the horizontal vertical basis. And the bit value that he gets is a 1. After they exchange a ton of bits, and they announce what bases they used for each one, they'll see that they chose the same basis. And so then what they'll know is that they have the same bit. And that means that they know that they can use that bit in the key. So they'll keep that bit, and that'll lead to a bit that they use in their key. However, so let's sort of look at how that works again. So this whole idea of announcing what bases they used, you might think, well, then they're kind of giving away some information. This might be really important information, and they're just publicly broadcasting it. Everyone can see it. Any adversary can see what bases they use after they've exchanged a whole bunch of bits. But we can very quickly see that that doesn't actually tell any adversary anything about the key that was chosen, because if, for example, Alice chose to measure something in the horizontal vertical basis, well, there's one basis vector that corresponds to the 0 bit, and there's another one that corresponds to 1. So if someone knows that that was the basis that was used, the bit that was obtained could still be a 0 or a 1, which means they still don't know anything about the bit that was exchanged. So what this basically means is that they can exchange a series of random bits, and just by announcing what basis they chose, they'll know exactly which bits they agree on. And from those bits that they agree on, they can extract a key. So we see here, if we go through some more of these, I'll send you guys this slideshow so you can look at this picture a little more. I think it's a very nice schematic, but you can go through all these and you can see, okay, so here, Alice prepared light in this basis and Bob measured it in this basis, so they'll realize that that's not part of the key. And then this time they measured things in the same basis, so they'll keep it, and they measured the same basis, so they keep it, measured in the same basis, so they keep it. But here, they measured it in the wrong basis, so they don't keep it. Now here's something interesting kind of happens. So we see Alice prepared a 0 right there, and Bob actually measured a 0. So they had the same bit. But the problem is, without announcing this bit, there's no way for them to know that they have the same bit, because they'll announce that they measured in the wrong basis. So Alice will say, I prepared this bit in the horizontal vertical basis. And Bob will say, oh, well, I measured it in the diagonal anti-diagonal basis. And they'll say, ooh, well, then that means that there's a 50% chance that we don't have the same bit. And the only way that they can know if they have the same bit is if they announce it. So even though they do have the same bit here, they can't use it in their key because they don't actually know if they have the same bit. So they have to discard this one anyways, even though they happen to share the same bit. But then again, you see here, like they measure in the same basis. So they know that once they announce their bases at the end of this whole distribution setup, they'll know that they can then use that bit for their key, and that any adversary won't actually have access to information about that bit. So by going through like this, what they'll do is they'll send a whole bunch of bits with a whole bunch of randomly chosen bases. And then after doing that many, many, many times, they'll then announce all of the basis choices that they made in order from the very beginning. They don't announce it immediately afterwards. There's some interesting actually adversarial attacks that show that that's a very bad idea, but essentially that's what they do is they prepare a whole bunch of bits, and then right at the very end, they announce what bases they chose. And that's essentially the gist of BB84. So the very last part that I mentioned is bit sifting. I'll just go over this again because it really is important. So right at the very end of their exchange, once they have a ton of bits that have been shared between them, they both announce their bases publicly. They announce it over their classical channel. Everyone can hear exactly what they're saying. It's not secret. Everyone knows exactly what bases they chose. But they announce their bases publicly. And then what they do is they discard all the bits where they disagreed on their basis choices. And the reason for this is because if they disagree on the basis choice, there's a 50% chance that they don't share the same bit. However, nowhere in this process do they actually announce any bit values. And that's really crucial because if they were to announce bit values, then it would be known very, very quickly exactly what their key is. So they don't announce any bit values, and consequently, they're able to maintain the integrity of the key that they've tried to set up an exchange. Yeah. So and the other thing is both different distinct bases have two orthogonal values, right? So we saw in the diagonal anti-diagonal case, we've got two basis vectors that are orthogonal like this, and in the horizontal vertical they're like that, and the diagonal anti-diagonal one they're like this. These are the two basis vectors, and you can see they form 90 degrees with each other. So there's nothing like this. This bit is not at all like this one. This bit is not at all like this one. But if we were to impose this, like superimpose this, we'd see that this is 50% like both, and this one's 50% like both, and vice versa. So really, like, just by knowing the bases, you have no information about the bits that were actually exchanged. However, if both parties did measure in the same basis for a given measurement, they know that the bit that they share for that measurement is the same. So they can keep that bit and they can use it in a key, knowing that no adversary knows what bit they have. So the adversary Eve, who's eavesdropping, doesn't gain any information about their key during bit sifting. Another cool thing about this protocol is it actually allows Alice and Bob to detect adversaries. So here's how that works. So Alice prepares her bit. So for a given bit that they want to exchange, Alice prepares that bit in a certain basis, and then it crosses through space and arrives at Bob. Once it arrives at Bob, it's fine because we assume that the adversary can't tamper with Alice or Bob's devices. So once it's at Bob's end of the setup, we know that that the bit is safe. But until then, some adversary, Eve, could very easily find that basis, or sorry, not the basis, could very easily find that bit in transit and could measure it. But the thing is, Eve doesn't know the original basis choice that Alice chose when she prepared that bit. And that's really important because then what that means is that if she wants to measure it, she also has to randomly measure it in a random direction. So let's say that there's an incoming bit that's polarized like this, and Alice measures it like this. Then when it leaves Alice, it's polarized like this. And so when Bob measures it, if he measures it like this again, if they announce their bases, so this is Alice's basis, and this is Bob's basis, or sorry, I guess this would be Alice's basis, and this would be Bob's basis, because you have to have both in the basis. But if Alice prepared that bit, and Eve then measured it to be in this direction, then Bob would be measuring this polarization rather than the one that was sent by Alice. And so half the time, this will be measured in the wrong direction. And what this means is that a large number of the bits that they get for their key will actually be wrong. So what'll happen is when they carry out their classical error correction for the key that they've distributed, Bob will notice that he has a very high error rate. And consequently, both Alice and Bob will know that the key that they tried to exchange has been compromised. So that means that they just won't use that key and they'll try again until they get a key that they can use, until they know that they're not being listened to by an adversary. So Alice and Bob, for their error correction, they randomly select certain bits and they announce those random bits publicly. Those bits get thrown away. The bits that they announce publicly get thrown away and they're never used again. They're not used in a secret key. But they randomly pick some bits and they announce them publicly. And some of them will probably be wrong due to experimental error. For example, if you're sending polarized photons through a fiber optic cable, it's known that fiber optic cables actually slightly change the polarization of the light along the way. So there will be some bits that are wrong due to that, or there will be some that are lost and stuff like that. So they'll see that there will be experimental error. And so they'll see that there is in some error rate in their key. Not all the bits will be the same. However, if they see a certain number of errors, if they see at least a certain number of errors, then they know immediately that there's been some kind of adversary, and so they know that they just can't use that key anymore. Now, so in this attack that I showed where Alice just straight up goes in between the line and randomly chooses a basis and reads the bit that's en route, they'll see an error rate that's at least 25%. That can actually be reduced if you use certain very clever attacks on Eve's part. However, I think the minimum threshold is 11%. So if you see an error rate that's more than 11%, you know that there's a possibility that there's an adversary, so you can't use the key anymore. So basically what this means is, to summarize this whole thing, by looking at how, by taking a subset of their key and I guess destroying it because they can't use it anymore, by publicly announcing it, they can then see how many errors they have roughly. Like they can see a statistical distribution of how many errors their key has. And from that, they're able to determine how likely it is that there was an adversary. And so they just say, okay, if this error rate is past a certain threshold, we'll throw away the key and start again. So Alice and Bob can always detect an adversary if there's one. And that's really crucial because that makes it very, very challenging for any adversary. In fact, it makes it impossible, in principle, for any adversary to learn their secret key. And that's why this really is an information theoretic secure protocol. Because no matter what, one of two things happens. Either the adversary cannot learn their key, or they don't use the key because they know the adversary knows it. So those are kind of that's kind of how this works. And you can see it really is quite a clever system, because it uses the laws of quantum mechanics, this whole idea of superposition, in such a way that if anyone tampers with it, then they'll see that someone tampered with it. And I think that's really clever. That's why I find it really interesting. But yeah, so that's roughly what the BB84 protocol is. And everything else in quantum key distribution, most things are essentially variants on that. So now I'm going to talk a little bit about entanglement-based quantum key distribution. This is fairly similar, actually, to the BB84 protocol. Again, the setup, we have to have an authenticated classical channel. The biggest difference here is that the open quantum channel is not actually from Alice to Bob, but it's from some third party, some third source that sends bits to Alice and Bob. So the protocol that we're dealing with here is that we've got this source, and what this source does is it emits pairs of entangled photons and sends one to Alice and the other one to Bob. And remember, when we talked about, and these are prepared in a random basis, and Alice and Bob then measure them in a random basis. And again, we go through basis choice announcement and bit sifting and error correction and all that, just as in the other protocol. But the really cool thing here is, because we're using entangled photons, if Alice measures her photon to be in some state, then Bob will in turn, she knows that Bob will measure his photon to be in the same state as well. So just by virtue of the fact that they're using entangled photons, as soon as Alice measures her photon, she knows exactly what bit Bob has, and they know that they share that bit. And if someone measures it en route, then again, you can use the same argument that if they won't know what basis Alice and Bob are going to choose, and they won't correspond to the same ones that are announced and all this. So again, they can use the same kind of detection system to see if there is actually an adversary. The biggest problem with this setup is that you have to trust the entanglement source. So for example, you need to trust that the bits that are provided actually are entangled, and you also have to trust that the source that's creating them doesn't measure them in advance. So like if you have somebody if you've got a box that's sending you what you think are entangled photons, but they already know what the states are, then they can keep that information and they could sell it to a third party or whatever. So you really need to trust the entanglement source. But beyond that, it's essentially the same as BB84. Here's a little diagram to illustrate it. So we've got a source here in the middle, and this source creates pairs of photons. This Greek letter psi represents like that sort of the common symbol to use to represent quantum states. So the source sends one of the photons in that state to Alice and the other one to Bob, and then Eve can intercept the line in between Alice and the source, or between Bob and the source. But because the particles are entangled, Alice and Bob will have correlated keys all the time. So they'll be able to know, again, in the same way in the BB84 protocol, they'll be able to see exactly what the other person has, and then when they do error correction, they'll be able to see if anyone tampered with the bits when they were on their way. So I'm going to talk about some interesting applications of QKD currently. So this is a neat schematic. So it's a little hard to see, but up here in the top left corner, this is actually the very first setup. So this was the one that was done in the lab by Bennett and Brassard in 1984. You can see this side of the table is Alice, this side of the table is Bob, and they were literally sending light. I think it's like 86 centimeters or something, like less than a meter across the table is how far they were sending their key. So this really isn't practical for technology, but it was a proof of concept. They showed in the lab that this protocol could actually be carried out in practice. I actually ended up building something a little similar to this a little while ago, and you can make neat little toy models of it just to demonstrate that the concept is functional. But then things have gotten a lot more interesting since then. So here, this is a group in China actually carried out an experiment where they sent, I think it was entangled bits. No, sorry. So this is the standard BB84 protocol, but they sent it to a hot air balloon that was moving in the air. So it's a big difference from here to here, because this is kind of just in a lab on a table in a very isolated, controlled environment. This is out in a hot air balloon moving through free space, several kilometers between the source and the receiver. And similarly, there were experiments that were done in the Cayman Islands, between two islands called La Palma and Tenerife, that are 144 kilometers apart. And this, I think, for a while was the record. But they were able to exchange a key, a secure key, between these two islands, almost 150 kilometers apart, through free space. This is just atmosphere. It's just regular breathable air in between them. And they just had a really strong laser that was connecting the two, basically. So this is really cool, because this is actually like quite a practical implementation of this. This shows that it might actually be possible, rather than to get away from just these laboratories, it might be possible to implement this quite realistically. And in fact, lots of people are. So this is an image. This is actually a commercially available quantum key distribution system. This is the Clavis 2 system by ID Quantique, which is a big company. I think they're based in Switzerland. And I think in Geneva in Switzerland. And what they do is they manufacture these quantum key distribution systems for private use. So banks could have a sender at one branch and a receiver at another branch, and vice versa, and they would connect them via fiber optic cables. And through those fiber optic cables, they would send their polarized photons and stuff like that. So, and what's really cool about this is this has actually been implemented very successfully in Switzerland. In fact, I forget, a few years ago, the Swiss national election, actually how they sent the votes that were counted securely to one central place was using one of these systems, was using an ID Quantique commercially available public key encryption system. I don't know how much it is, but if you have, I think, like hundreds of thousands of dollars or a couple $1 million at your disposal, you can literally just go and buy one of these. And it's just a plug and play system. You just set it up and you're good to go. There's no finicky physics that you need to do, no laboratory work that you need to do. It all just works. It's just an out of the box system that you can plug in, and it works. You can do public key encryption with it. Then another cool thing that's going on right now, this is a group of researchers in China who actually just over a year ago, in August of 2016, successfully launched the first satellite-based quantum key distribution system. So this is this is the satellite that they launched. It's quite heavy, and it's several tons, and it costs them quite a lot of money. But basically, this establishes, I can't remember. It might use entanglement-based quantum key distribution, or yeah. Basically, this sends entangled photons to two different locations on the ground, several hundred kilometers away. So, this is of course moving through space. And the idea is, if we can set up different satellites that have this kind of system on them, we can create quantum key distribution systems between many different nodes all across the planet. So this is a really big step, because this is sort of when quantum key distribution became something that we could conceivably see as similar to the internet in its ubiquity. So this is really quite a big result. And actually, just to go back to this for a second, hopefully in a few years, there's a Canadian team as well at the University of Waterloo, headed by a very distinguished researcher named Thomas Genuine, he's essentially trying to do the same thing, but with a much smaller satellite. I think it's going to weigh about 50 kilograms. It's very, very small. And they've been doing a lot of tests with it. They've got their system working, and they tested it from ground. They tested ground to a moving truck, which is of course very difficult. Not as difficult as ground to a satellite, but they were able to establish a key between the ground and a moving truck. And more recently, they actually were able to establish a key with this setup between the ground and a moving plane. So they're really making a lot of strides in this research. And I think in the next few years, it's only going to get better, and it's going to take off more and more. So this is really a growing field. There's lots of people that are really, really interested in this. And it's only going to get bigger. It's still in its infancy, and I think many people believe it will be very ubiquitous in the future. Yeah, so now I'm going to talk about some really cool things in quantum hacking. So there's a guy at Waterloo named Vadim Makarov who's kind of the wizard of quantum hacking, if you will. He's really quite good, and I was there for some things just this past summer, and he gave some talks on quantum hacking, and I was really interested by it, so I thought I'd share some of it with you guys. Basically, what he does is he goes to those companies that make like for example, ID Quantique in Switzerland. He goes to those companies and or buys their commercially available quantum key distribution systems, and under big non-disclosure agreements, he then hacks them in his lab about the problems that he found and hash them before he then publishes his results in a journal, which is really kind of cool. So I'm going to talk about a couple of the big attacks that have been sort of found. This one's more of a theoretical attack, but some of them are more practical. So this is called the quantum number splitting attack. Let's say that Alice is trying to send a key to Bob, and she's using single photons. So it's possible to create single photons in the lab. That's been done. There are several QKD systems that use single photons. But let's say that she's sending single photons to Bob. How single photons production works is you're not exactly getting one photon every time. You're usually getting one photon. On average, you're getting one photon. Sometimes you'll get 0. Sometimes you'll get 2. Very rarely, you'll get 3 or 4. So it's not precisely one photon. And in fact, it can't be precisely one photon. You can show that mathematically, that you can't ever create exactly one. You can't know that you've created exactly one photon. Like you can't just say, I'm going to make one photon now. You have to say, I'm going to make an average of one photon now. And sometimes you'll get too many, sometimes you won't get enough, that kind of thing. So, so let's say that Alice is sending approximately single photons to Bob. And then Bob detects single photons and determines the key that he has after sifting and doing error correction. Well, this seems like a perfectly reasonable thing to do, but there's a very interesting attack that Eve can carry out. So suppose Eve has technology available to her to count how many photons have been emitted. So a photon number counting device. These don't exist in the lab. They're not robust enough to use for anything like this. But in principle, they're possible. So we have to assume that Eve has this device, this magic device. She counts the number of photons that are emitted every single time she emits a photon. Keep it herself. She just redirects it somewhere else, and nobody ever sees it again. Now, let's see if Eve detects more than one photons. So she's got 2 photons. 2 photons. And what she'll do is she'll keep one, and then the other one she'll send along to Bob. So now what will happen is, and then the one that she keeps, she'll store in a quantum memory. So she won't actually measure it right then and there, but she'll keep it in a container in a way. She'll hold on to it for later, and she won't measure its polarization. So then what will happen here is Bob will measure a single photon. Admittedly, he'll get a much lower rate than he's used to, but that could be due to high losses in the channel or whatever. So Bob will see a much lower rate in how many photons he's detecting because most of the single photons are being thrown away by Eve. But whenever he does detect a single photon, he'll of course randomly choose a basis and measure it, and then they'll both announce their bases afterwards. The problem is, once they announce their bases, Eve knows what the basis choices were for each photon. So she has this photon stored in memory that hasn't been measured, and it's in the same state as the one that Bob measured. So she can then measure the state of this photon in the basis that was publicly announced by Bob, value back. In this way, Alice and Bob will never know that she actually was. All that they'll know, they'll assume that they had a highly lossy channel, and then they'll assume they have a secret key. But Eve will actually have exactly the same key as they do. So this is an interesting attack. Practically, it can't be implemented yet by any hackers or anything like that, but it's a very interesting attack. And it has to be considered for the future. Possible countermeasures for this would be looking at, for example, sort of a standard efficiency rate. And then if you see that drop down substantially, then you know that there's someone doing an attack like this. So there are countermeasures, but it shows some of the subtleties that you have to consider. So just to show this again, let's say we've got Eve, who's emitting single photon, or sorry, Alice that's emitting single photons, and Eve is some adversary in the middle, and then Bob on the other end. So these are single photons. Occasionally there will be two. Whenever, what Eve will do is she'll throw away all the single ones. But whenever she sees two, so let's say when these ones get through, one of them will go to her quantum memory, and the other one will go to Bob. So Bob will see a much lower rate, but he'll still detect photons. And so the one that went to Bob, let's say Bob measures it in the horizontal vertical direction. And let's say it was prepared that way by Alice, so it's a bit that they keep. Then what Eve can do is she can then measure hers in the horizontal vertical basis as well. And in doing this, she'll obtain the same bit value that Bob got and that Alice prepared. So in this sense, Alice and Bob and Eve will all share the same key, but Alice and Bob won't know that Eve is there. Another cool attack is called the Trojan horse attack. And how this one works basically is Eve is always allowed to read and write to the quantum channel, right? That was one of the axioms that we supposed in the very beginning. So because of this, in optical implementations of quantum key distribution, this essentially means that Eve is allowed to send in her own light signals in either direction of the channel. So she can send her own pulses of light to Alice's apparatus. She can also send her own pulses of light to Bob's apparatus. This is one of the attacks that I think Makarov's group actually successfully implemented for several different systems, and it's really cool. One thing that we have to know about practical systems is that every optical component, even a totally transparent lens or any kind of surface that light passes through, it's intrinsically reflective. So it might be that 99.999% of the light that hits a certain lens passes all the way through that lens. But that tiny little bit that doesn't gets reflected. So what this means is that you can always get back reflections. So let's say Eve has a whole bunch of optical components like this, whatever, and she sends in a pulse of light, and it goes like this. Or sorry, this is Alice. Well, what we can do is we can then have Eve. Eve can do something similar. Eve can actually send in her own pulse of light. So I'll say the blue one is Eve's. So Eve can send in her own really strong pulse of light. So Alice's might have been a very weak pulse of light, single photons, whatever, but Eve can send in this massive pulse of light. And by sending in this huge pulse of light, it's going in this direction. Let's say that this component right here, the second one, let's say that that's where Alice, prepares the polarization of the bit that she's sending. So this is where essentially where the bit value gets chosen. It sends in a big pulse of light. Some of it will be reflected off of this surface, the first surface. Some of it will be reflected off the second surface. Some of it will be reflected off the third surface. But some of it will go through that component and be reflected off the surface behind it. So some of it will actually go like this. And the light that goes like that, of course, passes through here as well. So if Eve knows the timing that Alice prepares her bits, then if she sends in a huge pulse of light at the right time, some of it's going to get reflected, and some of it's going to be prepared in the same way that the bit that goes on to Bob is. And so then she needs to only measure that pulse of light. to obtain the same bit value that Bob gets. So this is really kind of a cool attack, because all she has to do is inject her own high intensity beam of light and store it in a quantum memory, and then once bases are announced, measure it again. And in this way, Eve can then obtain perfect knowledge of the key. Again, there are countermeasures to this. There are certain optical devices that you can implement that essentially only allow you to send in single wavelengths of light, and then it becomes very hard for Eve to distinguish which one's hers and all this stuff. So there are countermeasures, but it's kind of a very cool attack, and these are kind of the ways that quantum hackers are looking at breaking these quantum key distribution protocols. So here's another interesting situation. So let's suppose that Bob has two detectors. We'll say he's got one for measuring horizontal vertical light. So this is one detector, sorry about the image, and one for measuring diagonal and anti-diagonal light. Oops, sorry. So he's got two detectors, one for measuring in each basis. Or sorry, not for measuring in each basis, but it would be like he's got one for measuring, let's say we're in the horizontal vertical basis. He's got one detector for measuring light that's in the horizontal position and one for measuring light that's in the vertical position. This is how he differentiates between the different bits. And for example, there would be a beam splitter here that would send some of them there and some of them there. Now, let's say again that let's say that this is a single photon, or sorry, no, not a single photon system. Let's say that he measures a double click. So this one goes off and this one goes off at the same time. Well, now we want to ask, how do we process this event? There are several different ways that we could, and it seems a little arbitrary because this seems like it's obviously just due to an experimental error, right? Things are imperfect. Detectors have what are called dark counts, which are when they measure something even though there's no light there. There's a lot of stuff that can happen. And these are very complicated experimental setups, so it's quite possible something just went wrong and need a double count and stuff. So how should we proceed? Now there's two possible strategies. Either we can discard the events and say, well, this was probably an experimental error, and so we don't really care about these bits, they'll just increase our error rate in our key anyways. Or what we could do is we could assign random values to the events. And that seems a little weird because when we assign random values to these events, we're kind of introducing error where it doesn't seem like we really need to. We're adding errors to our key because if we assign a random value, then half the time we do that, the bit that we give is going to be wrong. So it seems like we're introducing error. So the second one seems like a bad choice on the surface. But then we realized that it's actually a much better choice than the first one because of a possible attack that a certain strategy Eve could use. So here's that attack. So let's say Eve measures the incoming photons in her basis. So she chooses some random basis. Now what she can do is she can emit tons of photons in her basis. So I'm talking like millions or billions of photons in the basis that she chose. Now what will happen is if Bob decides to measure the incoming photons in the same basis as Eve, only one of his detectors will click. But if he decides to measure the incoming photons in the opposite basis as Eve chose, then he'll get double clicks every single time because of these millions, half of them will be half of these many photons will be going into one detector and half of them will be going to the other one, because if he measures in the wrong basis, there's a 50% chance of either thing happening. So in this sense, if Bob were to discard these double count events, then he'd only be keeping the events where he shares a basis with Eve, which is really bad because then when they publicly announce what bases they had, Alice and Bob, then Eve will have the same bases as Bob, so Eve will share the key when Bob gets it. And so this is really, really bad. So what this means is we shouldn't throw away double count events. Rather, what we should do is assign random values to them, which will increase the error rate that we have in our key at the very end, but at the same time, it'll allow us to avoid this possible attack. And that's something that we have to watch out for. So here are some of the practical limitations of quantum key distribution. First of all, it has a very slow key rate, and this is kind of necessary just on how the system works. So we know from the one-time pad system that, let's say our message is length n. Then that means that our key must also be of length n. So our key must be of length n. However, we also know that since half of the time when Alice and Bob try to share a bit, they'll get that wrong, like they won't choose the same basis, that means that half of the bits are going to get thrown away. So they need to share twice as many bits as the length of the message. And furthermore, a whole bunch of them, let's say C, some constant C, those get thrown away due to error correction. So really, you need to create this many bits, which in order to encrypt an n-bit message. So you need to prepare way more bits than even the size of the message that you're trying to send. So this means that it's very, very slow to create a key in quantum key distribution. Furthermore, you'll see that you have very lossy channels when you try and do quantum key distribution over long distances. And so it takes more time to even exchange bits and get this kind of thing. So one of the biggest problems right now is trying to increase the key rate of quantum key distribution, because it's not like you're sending some small seed of a key that's much smaller than your message, where it might only be several bytes. You actually, if you're sending a gigabyte of information, if you want to encrypt a gigabyte of information, your key needs to be a gigabyte long. And so you actually need to prepare more than 2 gigabytes of, you need to try to create more than 2 gigabytes of key in order to even be able to encrypt that 1 gigabyte message. So very slow key rate, and the key has to be really, really big. So that's a big limitation right now. The other thing is we see systems have very high losses. There are imperfect channels, imperfect optical components. Increase the distance, the number of bits that you're exchanging decreases very, very quickly. So after several kilometers, you're really losing a lot of your key. So it's possible, as we see from the case in Switzerland, it's possible to send to use quantum key distribution to exchange information across distances, say within a city. Able to look at international telecommunications using quantum key distribution yet, because large distances have very high losses, and you still need to create large keys. Another practical limitation, and I guess this is also relevant in classical cryptography, is that an adversary Eve can always prevent Alice and Bob from communicating, because all that they have to do is put their own device in between. So Alice and Bob, if they detect that there's an adversary, they can't communicate. And so all you need to do is be an obvious adversary, and you can prevent Alice and Bob from communicating at all. Which means that if you want to, you can automatically prevent communication, at least secure communication, as an adversary. But that's kind of what you want in a good system. You want it to be that either someone can stop you from communicating, or they can't gain anything about your information. That's kind of the trade-off that you want, and that's what can be created, but it is certainly something to keep in mind. The other thing is, at the moment, it's technically very difficult to implement quantum key distribution. It's getting better because technology is always getting better. We're seeing lots of development with like chip-sized optical devices rather than the whole tabletop optical labs and setups. We're seeing things are getting much smaller. There's someone I met who's actually working on a project to implement QKD systems in like credit card size things for like going to a bank machine and stuff like that, which is really cool. So things are getting miniaturized and things are getting made faster and more reliable, but it is an uphill battle, and that's still definitely going on. So technically we're not at a point where we can really implement it on a large scale yet. That being said, most people are very optimistic for the future, but at the moment we're not quite there. So then there's the stuff that's going on currently in current research. There's a lot of people looking at quantum networks. So what they're trying to do is figure out, we see that if you're trying to communicate using quantum key distribution over long distances, you get high losses. So a lot of people are looking at different ways to network quantum key distribution with repeaters and stuff like that to try and extend the distance that you can actually communicate using QKD. Part of that is, of course, satellite QKD, which brings a whole bunch of other challenges that are much more related to aerospace engineering and things like that. But that's also a very interesting and very active field of research right now, which is kind of to help make quantum key distribution possible on a very, very large scale. Another thing that's going on right now is people are looking at what's called post-quantum cryptography. So when people realized that quantum computers could break current cryptographic systems, there were kind of two different branches that people went into. Most people chose to study quantum key distribution, but a smaller group of people who are doing a lot of very cool work actually have chosen to study what's called post-quantum cryptography, which uses a lot of very advanced mathematics and elliptic curves and lattice algebraic structures and stuff like that to essentially construct types of encryption that work in similar fashions to classical cryptography. They don't use any of this quantum superposition or anything like that. But what they do is they're looking at creating classical systems that have the same advantage as quantum key distribution. And the idea there is if you can do that, then you might be able to have faster key rates and things like this. And it might be easier to implement because you don't need to rely on the high controllability of quantum mechanics and stuff like that. So that's also a very interesting and very active field of research. Another thing that's kind of surprising is that it's very challenging to prove security for practical implementations of QKD. So theoretically, it's easy to show if you have an ideal system that it's perfect. And similarly, it's easy to show that even if you have an ideal classical system, it's not perfect. But the problem is showing that a practical system, like an actual implementation, is perfect. And it's hard to actually find a number for how secure practical quantum key distribution implementations are. So there's a lot of research going on. A guy named Norbert Lütgenhaus in Waterloo is a big proponent of that. Lots of people are working on that, actually. That's a big area in theoretical quantum cryptography at the moment. But that gets, I would have mentioned some more of that, but that gets into a lot of advanced mathematics, and you have to use things like entropy measures and all this crazy stuff. So I didn't get into that right now. But it's really cool, and if you're interested, I'd suggest looking it up. Another cool thing that's going on right now is called device-independent quantum cryptography. And this would be sort of the holy grail of QKD, because a lot of the problems with security right now that lead to these hacking approaches and stuff like that are that people are tampering with the devices. So Alice and Bob have their own sides of the setup, and those functionally work, but the practical implementations of both sides are not perfect. However, it's been shown that it's theoretically possible to create a kind of quantum key distribution that's called device-independent QKD that basically relies not on how well each side works, but rather you see Alice and Bob relying on some other source to give them their secret key. Unlike the entanglement version that I mentioned earlier, this sort of, I guess, this oracle that's giving them their key doesn't even need to be trusted. They don't actually need to trust this source, which is really cool because that kind of removes all of the possibilities of hacking. Because if the source tries to destroy their key, or sorry, if the source tries to learn their key, you can show that in this, it's very complicated, so I didn't go into it, but you can show that if the source tries to read their key, then it actually ruins the key and the parties can detect it. And similarly, if any adversary tries to detect the key en route, then they get the same result from the BB84 protocol where they can then see that there's an adversary. So here, we don't even have to worry. We can even assume that the adversary, Eve, is the one that's giving them the key. And therefore, we don't have to rely on any practical implementation hacking. Like there's no Trojan horse attacks. There's nothing like that that can violate it, because all of the trust, there's no trust that has to be given to the sources. Essentially, all that's happening is Alice and Bob are measuring bits. And that's really cool, but it's shown that it's very, very difficult to implement practically. So So that's a big area of current research. There's also a lot of people researching quantum hacking right now because it's a really cool field too. But yeah, so that's sort of a summarization of quantum key distribution, some of the theoretical aspects behind how it works, why it's necessary, and where it's going in the future. So now I think, yeah, we can take some questions now. That's what I had prepared.
Thank you, Patrick. You rock.
No problem.
Let me try to activate the cam. Let me see. Jesus, how can I activate this? Well, anyway, if it works, then we continue with the image. Otherwise, we continue without it.
Okay.
Well, in our group, many people sent messages about mainly doing questions and then commenting about some of the topics. In some time, we even got in a discussion in the group. They were discussing while the presentation was happening. So awesome. I find it cool. And at the same time, it would be nice to answer all the questions. I think I have here 14 questions.
Okay.
Many of those are very complex. So I think they got really heavy.
Excellent.
But sadly, we don't have that time. We got a little over the time. So what I have in mind is I will give 2 of the questions, the first ones, and then the rest I will leave with you.
Okay, yeah, perfect.
And then you
answer to follow.
Right. So you answer it in a text or something, and then I publish in the event, and they will have access to it. Some questions I deleted because that's like letting it clear to the ones who are watching. I deleted some questions because he explained that in the video, and as this is being recorded, you can check it later, so you can reveal the video. There are some researchers that couldn't be here now, and they will reveal the video. So for those who weren't here while we were recording, you can still make some question, I think, and Patrick will respond later.
Definitely, yeah. Send me any questions that you have, even if it comes up in the next couple of weeks, anytime. I'm happy to answer them whenever.
So it's nice. Well, so the first question they had, I forgot the name of everyone because many people sent at the same time, so I don't know which is from whom. But anyway, the first question is, why does measuring change the state of the system? How practically you are disturbing that state?
Okay, so this is one of the really interesting subtleties of quantum mechanics, and it really gets into a thing. It's called the Heisenberg uncertainty principle. Is really the sort of pinnacle of this area of research. But you can look at it as like so a nice way to think of it is in classical physics, when you're considering large systems, moving planets or mechanical systems on Earth, like big things like that, when you measure them, you don't really disturb them very much. But when you're looking at things like atoms or electrons or things that are really small like that, the only way to probe them is with other things of like similar attributes. So you can't actually look at an electron with something smaller than an electron. You can't look at a photon with something smaller than a photon. So in that sense, if you're trying to measure some property of a photon, let's say you try and do so using another photon. Well, in order to get that to work, you kind of need to already know everything about the photon that you're using, right? And so in order to do that, you already need to know the total state of the photon that you're using. And to do that, you might have to measure it using another photon, and then you need to, so it's kind of, an infinite regress in that sense. So you never know exactly the state of the things that you're using. Like in the same sense, I mentioned that analogy with, for example, putting a thermometer in a cup of water to measure the temperature of the water. Well, it's not necessarily possible for you to actually learn the temperature of the thermometer before you put it in the water. Because, I mean, in classical physics it is, but the analog of that in quantum mechanics is that it's not possible to know the exact state of things that you're using when you're using them as a measurement device. So as soon as you try to measure something, you're kind of assuming that you already know everything about the tools that you're using to measure. But those tools are subject to the same laws that you're trying to measure in the first place. So you can never really know everything about the system. And furthermore, this is kind of much subtler. And if you'd like, I can send you some nice mathematical proofs about this. But there's a thing called the Heisenberg uncertainty principle, which basically says that for certain properties, not everything, but for a lot of quantum properties, for example, it works with position and momentum. The more knowledge that you gain about one of those, the more uncertain you have to be about the other one. And this isn't like, this doesn't have anything to do with measurement devices. This is literally just like, the more that you confine the true state of something to a point, in like, for example, the more you say that this particle is in exactly this position, the less you can say, I know what the momentum of this particle is. And that's just fundamentally based on the mathematics that you use to describe quantum mechanics. And what's really weird is that you actually see stuff like this in the lab. So for example, I'll use position again because that's a nice example. Let's say you really, really want to know the position of a particle. So you put it in a smaller and smaller box. Well, what ends up happening is, because of that uncertainty relation that you can define mathematically, it says that your knowledge of the momentum gets much more uncertain, which essentially means that it's moving faster. And it could be moving really fast or really slow. You have no idea. But if you look at it the other way, if you try and measure very specifically the speed of the particle, you don't know very much about where it is. And this kind of thing leads to what's called quantum tunneling. So if you confine a particle to a box and you try and measure how fast it's moving, because you lose certainty about where it is, sometimes you'll actually find it on the outside of the box. Even if the box is supposedly impossible to get over the wall, you can find it on the outside of the box just because there's a necessary restriction of how much you're able to actually know. And this is one of the really sort of unsettling and disturbing aspects of quantum mechanics that makes it really weird. This is kind of what makes quantum mechanics much more philosophical than a lot of other sciences, is that it really does mess with your head and it really does have some weird interpretations. And it's not at all clear exactly what it all means, but we do know that there is fundamentally a restriction on our knowledge of a state. And when you try and measure a state, your knowledge of it actually changes in such a way that the state changes, basically. So I think I've kind of got off topic there, but whenever you try to measure a state, the very act of how you define measurement within quantum mechanics necessarily requires that you change what the state is in a way that you can't predict. So it kind of boils down to a coin toss. It's random in some respects. When you measure something, the outcome, it's not totally random. There is certainty, but it's random in some respects. So I guess that to answer your question, whenever you try to measure something, you can never be certain of the outcome that you're going to get. And you never know what you're starting with. So whenever you try and measure something that you don't know what you're starting with, that measurement will actually change what you actually learn about it. So I'm sorry if that wasn't clear, but that's kind of roughly how that works. I can send some follow-up documents about that because it gets really complicated, and it's very it's one of the big subtleties of quantum mechanics that makes it a very very cool field, but also a very conceptually difficult field to learn. So yeah, so I hope that answered your question. I'll try and send something along as well to John to follow up with that further if you're interested. So, yeah.
That was nice. What the hell? Okay, I think now it's working. Well, I changed my mind. I think I would do some other 2 questions because I saw that many of the questions were about specific topics or images on slides. So
okay.
In order not to make you come back to the slides, I will ask you the general questions they had, and the other I will leave you to answer them with written answers.
Sure thing.
Well, the second question is, that's a very good question. I will I will make sure to pay a close attention to the answer. But the question is, Thomas Young's double slit experiment found out that the particle behaves like wave when not observed. It's already clear why. Okay, the particle is behaving like a wave, but why? Why does that happen?
Okay. Let's see. So the thing that we're looking at here, here, I'm just going to switch back to my screen so I can kind of write some stuff out. The thing that we're looking at here, so I mentioned that we kind of represent quantum states by vectors, right? And how we kind of describe the probability of certain things happening is by taking certain elements of a vector and squaring them. So I won't get into the specifics. This is all, I hope this is somewhat conceptual, but we take a certain quantity, which we denote like this, and we take the square of it. And that kind of gives us, that's a probability, right? So that kind of tells us how likely it is that a certain event that we denote by psi is going to happen. Now the thing is, if there's two possible events, which could mean a particle going, like let's say we've got a double slit set up like this. If there's two possible events, and by this I mean the possibility of the particle going through one slit, or the possibility of the particle going through the other slit, those are both two different possible events with their own distinct probabilities. And what's weird is that we can represent these then as superposition states. And the way that we do that kind of introduces a weird minus sign. And this minus sign that comes in, so a superposition state takes the form of like A plus B plus C dot, 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 for all the different things that it's a superposition of. But what happens is, if we're trying to add up all the different possibilities, so like let's say we're considering the probability of the light arriving at some point on the screen in the back. So the probability of the light landing there, or the light landing there, or the light landing there, or whatever. So the light that goes through the first slit has a certain probability of hitting the wall here. It also has a certain probability of hitting the wall here, and also a probability of hitting the wall here. So the light that goes through here, although most of it will hit the wall here, it's got probabilities going everywhere else. Similarly, the particle of light that goes through this way has a probability of landing here and here and here and everywhere along the wall. But the thing that's weird is that when we kind of actually express these in terms of a superposition state, we kind of introduce a minus sign, which is really kind of strange. So if we were to square the different possible places, like, so this corresponds to an event. So we say like the event of the particle landing on at this point, or the probability of the particle landing at this point, or like that. If we were to square those events and then add them to get the total probability of stuff happening, then what would happen is, because of this squaring, all of the minus signs would go away. But what actually happens is, like this, isn't very rigorous, but what actually happens is we kind of square all of it rather than just the end. Like we don't add them in square. Like we don't add the squares. We add the parts and then square the total. And so what happens there is, if this is a minus sign instead of a plus sign, which is it's allowed to be, or if this one's a minus sign, for example, whatever, then terms in this will actually cancel. And so then what we'll see is there's actually certain places here that have zero probability, because like that event, there was a positive probability of it happening and a negative probability of it happening. They're the same, so they canceled out to be zero. So that's why we see these fringes that appear on the wall at the back, the sort of bright spots and dark spots. And the thing is, it's not saying that light itself is a wave, but rather it's saying that this phenomenon can equally well be represented in terms of waves. So we can express this in terms of waves. I'm sure you'll see that in high school physics, for example. There's some good reasons explaining, like if you assume light is a wave, you get that automatically. But even if you assume light is a particle, and you treat it quantum mechanically, you still get this end result. So you can kind of see in that respect that whether light is a wave or not, it exhibits wave-like properties. And that's kind of the key point, is that when we actually look at quantum mechanics, this is probably one of the weirdest things I'll say all evening, is that when we look at light, for example, there's a lot of people who talk about light being a particle and a wave-particle duality, all this stuff. But it's more than that, because light actually is neither a particle or a wave. It really isn't either, because we define a particle to be something that's localized, and we define a wave to be something that's spread out. And of course, depending on how you look at light, depending on the way that you're using it, it can be both. We see cases where light behaves in this way, and we see cases where light behaves this way. So we can't very well say it is a particle or it is a wave. Some people say that that means it's both, but really a better way of looking at it is that it's something totally different. It's very, very abstract. Particles don't really make sense because they can behave as waves. Waves don't really make sense because they can behave as particles. So it's not so much that we have things that are both particles and waves as much as it is we've got these much more abstract objects that exist that if we were to look at them through, I guess, a classical lens, sometimes they look like they're particles and sometimes they look like they're waves. But those are the words that we have left over from classical mechanics. Those are the words that we get from classical physics. So they're sort of a permanent part of our language. So it becomes very difficult for us to try and talk about things that are neither particles or waves of physical objects that are like that. But in fact, that's how it is. And if you look at more like philosophy of quantum mechanics and things like that, there's a lot of people that look at the true ontology, like the true way that things actually exist in reality, and most people will agree that it doesn't really, it's a nonsensical notion to even call something a particle or a wave. And in fact, there was a scientific revolution after quantum mechanics that led to what's called quantum field theory, which was the idea of sort of meshing quantum mechanics with special relativity, Einstein's theory of relativity, not general relativity, so it doesn't include gravity, but everything else. And what you get out of that is you actually don't get particles or waves. You get these things called fields that permeate all of space, and excitations in these fields correspond to what we would classically call particles or waves. So it becomes a lot weirder. So I guess the short answer would be that in the double slit case, we see that just because of how the math works in the quantum mechanical description of particles, I say particles in quotation marks, where certain probabilities cancel each other out and become zero. And then because of that, you observe what looks very similar to a wave-like phenomenon, which is why we look at light often as being a wave. It's very fair to treat light as a wave in many respects. In the same way that in other ways, probabilities cancel in such a way that particles or light appears to be a particle. But really the important thing to realize is that this is convenient language, and of course I am guilty of using the word particle all the time, but fundamentally speaking, light is neither a particle nor a wave. And when you really get into the heart of quantum mechanics, you can't really say that it's either of those, which is kind of, I guess, more of a philosophical point, but it's pretty cool. So I think that kind of answers your question. Yeah.
I find it nice the way you explained it, mentioning the mathematical, because the mathematical part will explain that. Once you have in your mind what's happening physically, it doesn't make sense because it's very abstract. But once you put it in the paper and try to experiment it in terms of mathematics, it becomes clear. So I think it was a nice approach. Well, let's go to the last question.
All right.
The last question is a question from my girlfriend. She's studying economics and she knows nothing about quantum cryptography, but even then she tried to watch the whole presentation.
Wow.
And she had a question. So I found it nice.
Yeah, definitely.
I found it nice. Well, the question is, what's the importance of the first methods of cryptography, or ciphering, as I like to mention, from the Second World War to nowadays, with quantum cryptography theory and other classical cryptography theories that are modern.
So what's the significance of the older techniques?
Yes.
Okay. So those older historical methods, if you saw like the movie The Imitation Game about like the Enigma cipher from the Second World War that the Germans used, things like that. Those were.
I think she was trying to give a reference to Alan Turing and stuff.
Yes. Yeah. So if you look at those classical cryptography schemes, they're really interesting because in those days we didn't have the technology that we have now. So it was not possible for us to exchange keys in the same way. If we ignore all of quantum mechanics, even just in classical cryptography, it wasn't really possible for us to exchange keys in the same way that it is with regular computers now. So consequently, we got a lot of different ways to try and secure data. And actually, a lot of what they did, although it was quite effective because of the lack of technological advancements in the time, in today's world where computers are really fast and powerful, they wouldn't stand a chance, is they use a thing called security by obscurity. And this is basically the idea of trying to make data secure and make sure people don't know what you're talking about by just making it really hard to figure out what you did to encrypt it. So this whole idea of, like, for example, the Enigma machine, that wasn't even theoretically a very good cryptographic system. The only thing that made it good is that people found it very, very challenging to figure out how they generated their keys, because that wasn't at all obvious. Another example of this is, for example, on like the American Army, for example, they employed the help of the Navajo Native American people because they've got a very distinct language that's very unlike any other languages in the world. And so what they would have is they were called the Navajo code talkers, and they were basically, they'd have someone on the front lines and someone in North America, and over the phone they'd speak in their native language, talking about what both parties wanted them to share. And because the Germans, for example, didn't know that language, they were unable to decipher it. So it wasn't so much a theoretically secure system as it was the technology available at the time wasn't able to figure out how the keys were being chosen. So the ways that those systems were secure they were strictly secure because we didn't have computers. There were no computers at that time, I guess, by the modern definition. And that's what led to the invention of the modern computer, because Alan Turing, of course, was one of the founding fathers of computation in its modern sense. So it was really through trying to, like, people realized at the time that they weren't theoretically very good systems. It's just that they were so convoluted and so figure out that they needed computers. And as soon as they have a computer, they can break it very easily. But since they didn't have computers at the time, they were very effective. And that's how they got through an entire war, using systems like that. But in today's society, cryptography is much more based on for computers to figure out things. That's kind of the biggest point of modern cryptography, is you want it to be hard for a computer to try and figure out what your key is. Whereas back then, since computers weren't an issue, they didn't exist, they didn't have to worry about that as a threat. So I think that's kind of the big distinction between cryptography in that time versus cryptography now, if that makes sense.
Yes, it's totally true what you said. And I think I have a question here, which is very simple to answer. So it's very objective, it's very direct. So I will also put it in the table. Someone, I think Vinicius asked, what is an open quantum channel? He didn't answer.
Okay.
He didn't.
That's a good question. So when we talk about channels of communication, I guess, so like classical channels of communication would be like talking to someone face to face, that's a channel of communication. Talking to someone over the phone, that's a channel of communication. Sending an email, that's a channel of communication. That's kind of what a channel is.
Yeah,
so we define
on classical physics, on classical cryptography, it's kind of intuitive to think about an open channel when you have the basis. But when you're talking about quantum and you're talking about light traveling and communicating, it gets a little confusing.
Yes, yeah. So the big distinction with the quantum channels is that so the classical channels, like with the telephone or the email channels, those sort of use classical information, whereas quantum channels are sending light that's encoded using quantum mechanics, using that whole idea of choosing a basis. That's sort of a quantum phenomena. So that's what we define as a quantum channel, is a channel that uses quantum mechanics as its mode of communication, rather than, for example, email that uses classical mechanics that run how the internet works, for example, to send the information. And what we mean by an open channel is that any adversary is free to read and write to it. So like, if you were to send, I guess if I were trying to communicate with you via, like, we'll say email, and over an open channel, then it would mean that someone would be able to inject whatever information they want into the email, and they'd be able to read whatever the email was. So that's kind of what I mean by an open channel, is someone's free to read everything that passes through it, and they're free to write into it as much as they want, or change whatever they see there already. Which is what makes the idea of quantum cryptography so powerful, is that all of the important information is communicated over an open channel. So anyone can intercept the information. Anyone can try and read it. We see that they fail to read it, but they can always try to read it. And they can always inject their own information. They can always change whatever they want. We see that that's a bad strategy for them, but they're always allowed to do that. And that's kind of what makes it such a powerful idea.
That's nice. So thank you very much, Patrick. You were like a hero to the students who were unable to understand many of the concepts in which we are like frequently passing through very fast, very quick. So it's awesome to have someone who also understands, who are a colleague, of course, and and I know very much, and I know there's a talented guy, and if it was a Brazilian, it would be here with us.
Absolutely.
So
absolutely.
Because of that, we would like to thank you in name of the group, and in my name, I would like to thank you a lot for accepting the invite. And you're free to come back every time you want, because you have a lot to teach us so far, and you are always studying, and you will always be capable of teaching us something new that we don't know. I would like to enjoy the moment to announce that we are going to Canada. Our group is going to visit the Institute for Quantum Computing. We are very proud of the projects that we are conducting here, and we hope someday in the future, and not a very far future, so maybe in December or January, we are going to Canada. We strategically selected the winter, as you may see.
Good luck.
Thank you. We're in winter now with like 34 Celsius, so we can't handle it anymore. We're giving up.
Yep.
We're totally giving up. So anyway, thank you. If you could receive us when we get to Canada, that would be nice.
If I'm able to, I would love to. That would be my pleasure. Yeah. And if you guys have any more questions, feel free to send them my way. I'd be more than happy to help you and understand anything that is unclear. So thank you so much.
I will send you the questions that are remaining. And if someone, I don't know, next week or tomorrow, watch the video and have a question, I will send you the link of the YouTube video where it is. So you can answer them in the comments below the video. And thank you very much. If you need anything, you can count on us too. And well, if you want to say something.
I just want to say thank you guys very much for having me. I think it was, I really enjoyed presenting for you guys. I'm really happy to be able to share a lot of this stuff. I'm very passionate about studying it, and I'm really to see other people that are also really interested in learning it. So I'm really sharing it with anyone who's willing to listen. So thanks a lot for inviting me and having me as your speaker. I thought it was
so awesome. Thank you very much, Patrick. We are going to talk more about our visit and our projects. I would like to show you something very cool that I have here. This is the book of Exma Optics. Here we have, I don't know if you are familiar with Exma Optics. It's one of the only companies that sells everything we need in terms of products to build a QKD system. So you can see, I don't know if it will focus, but it has my name. It's on my name. And
Nice.
here we have all the products and all the items we need, the material we need to build a QKD system. And one of the challenges we have here is to explain how they work and how they're specifically connected to make everything work well. And they have, I imagine they have difficult to understand many of the concepts, like the polarizers and stuff like that. So you're invited in a future opportunity to come back here to explain about the components of the QKD system.
I'd be happy to do that.
So thank you very much, Patrick, for your time. And
thank you.
I appreciate your help and everything you're doing for us.
Anytime.
So guys, I would just give a little ending in Portuguese here, so I will make it clear. Então, pessoal, valeu por assistir. Quem está no grupo do InfoSec está assistindo e não entendeu nada, pode ficar tranquilo que a gente vai colocar legendas. Quem entendeu tudo, parabéns. É muito legal esse assunto, é muito legal esse tópico de segurança da informação, esse tópico de criptografia quântica. Enfim, pretendo trazer ele mais vezes para falar sobre isso. Vamos continuar conduzindo os experimentos. A gente vai colocar no nosso site agora o novo site do grupo, e lá vai ter mais materiais. So Patrick, if you have any other material, advanced topics or something like that, PDFs, we would love to have it.
Sure thing.
And that's it.
Thank you very much.
Thank you very much. Goodbye.
Goodbye.